Thank you for the introduction. This is just a little bit of background about crowdsourcing. I don't realize that everyone in this talk knows crowdsourcing, so just some background. So this is a very popular technique for collecting labels for machine learning training data. And the problem is that the labels can be noisy, so the common practice is to collect many labels for each item and then to aggregate the labels to get a single label. This is a fun example. So for this picture, let's assume we have 3 labels from 3 crowd workers. And so if we just use majority voting, then the aggregated label is just a dog. So the crowdsourcing aggregation problem is a very popular problem in machine learning, and recently I know of at least 20 papers and probably more than that on this problem. So, in most of this previous work, the idea is the following, and this is a very simple idea. So they improve from majority voting by weighting by these estimates of this annotator performance. So if an annotator has a higher performance estimate, then their labels would be weighted more. So, and then also in this previous work, their aim is to improve aggregation accuracy, which is important. But in this work, we take a slightly different direction. So recently, there have been a lot of interest in explainable machine learning and explainable models. So we asked the question, can we make crowdsourcing aggregation modeling more explainable? So by explainable, we are specifically interested in explaining the errors by these annotators. So the question is why the annotators made mistakes. And yeah, so we would like to use an aggregation models to detect these patterns of annotation error. So these the key ideas in this paper is to combine aggregation and clustering. And so there are a lot of motivation for why we want to do this. In general, we want to understand the annotators better. So if we understand why they are making the mistakes, then we can provide, say, personalized feedbacks to help the annotators improve. And then for the requester, they can also revise the task instruction to get better data in future. So we consider this task in natural language processing. So the name entity recognition task is the following. So suppose you are given a sentence, Nguyen Graham gave a keynote talk at ACM in Los Angeles. So that was what happened this morning. And so given this sentence, the task is to annotate who are the person, the organization, and the location in this text. And so this is a very useful task in natural language processing. It is useful for many downstream applications in translation or question answering or conversation. And so we use this data set. This is a standard data set in the name entity recognition task. And we use the crowd label collected by that paper. So this is just an example of what an explanation would look like. So the words that a crowd worker missed. So these are basically the mistakes, annotation mistake in this name entity recognition task. So if we look at the first cluster, so you can see that this is mostly acronym and with some punctuations in the text. So probably they are being confused by punctuation. And the second one is, so these are all capitalized acronyms. And the interesting one is the third cluster, where you see a lot of nationalities. So these nationalities are usually in organization words, and it looks like this worker has some confusion about nationality. Okay, so again, this key idea is to combine aggregation and clustering. So we apply a very basic and very classical clustering algorithm. And in this David and Scheme, the classic model, this is so I just summarize, this is an iterative algorithm that alternate between estimating the true label and estimating the worker performance represented by confusion matrices. So that was the aggregation modeling, and for clustering, we also use a very basic clustering algorithm based on hidden variable mixture model. So in this model, the assumption is that the cluster ID are hidden variables and data generated condition on cluster and the cluster ID and parameters. So in graphical modeling, this is a picture. We have this aggregation model on the top right, and then we have a clustering model in the bottom left. And then the idea is to combine these two models together in the graphical modeling. So just some details on learning algorithm. We use expectation maximization and deep sampling with details on the paper. So our first experiment is on, this is a computational experiment on the quality of the cluster that we got. So we compare this to a baseline of basically just aggregating and then do clustering separately. So just a reminder, our method is aggregate and cluster in a single model, and this is separately. So and we use this metric on evaluating cluster quality. So in this data set, so we see that so first of all, the good news is that there are some improvement over the baseline. They are a little bit small, but it's good to see, and we also see that with more data, this improvement is larger. So that I think is good. So that was the computational experiment. And then for the human experiment, the question is, can people actually understand the cluster? So we have this task again on Mechanical Turk because it's easy to do. So with over 100 participants. So people are randomly assigned to 2 groups. In the first group, they see a list of correct and wrong annotation, and we call this a list group. And the second group is they see the cluster. So basically, this what cluster that I showed you earlier. So the hypothesis here is that by looking at cluster, so if you are a requester, you are trying to understand why their workers made mistakes. Probably what you do is you look at a list of correct and wrong annotations. And here we are trying to see if instead people look at cluster and see if they have a better understanding of why workers made mistake. So the task here is this is an objective task. It's just to predict future annotation by the same worker. We have 5 questions for each Mechanical Turk hit, and so they can just do 1 hit and quit, or they can just do as many as they like. A lot of people quit actually. So this is the results. So the x-axis is the number of answers. So this is like the number of questions that they answer. So as I said, there are 5 questions for each hit, and with 8 hits in total, we have a total of 40 answers. So say this is for 5, this is for people who just did 1 hit and then quit the task. So we plot this accuracy and 95% confidence interval comparing the list group and the cluster group for predicting, this is the accuracy for predicting future annotations. We have several observations. The first one is it looks like cluster is generally better, although not so good. The difference is small. So and then we also observe that this is a difficult task, and in general we have very quite low accuracy. Another observation is whether people just did 1 hit and quit, or they did everything. We don't see a big difference in their performance. Yeah, so for conclusion, crowdsourcing is a very popular mechanism for collecting labels, and there have been a lot of work on aggregation modeling. So in this paper, we see this as a step toward more explainable crowdsourcing aggregation, and we have the key idea of combining aggregation and clustering. There are some promising results, but I also acknowledge several limitations. So This is a difficult task. We have small numerical difference, and the cluster sometimes very difficult to interpret. So just one idea for future work is to have more interaction to get better clusters. So I also acknowledge the Mechanical Turk's participants, the reviewers, and NSF. And it looks like I finished early, so we have time for questions.
Questions? Well, I'll start. Oh, got one.
Hi, Walter Lasecki, University of Michigan. I was just wondering, so you have this limitation here that says clusters are sometimes hard to interpret. I wonder if you thought about adding in some level of explanation, so the person doesn't just give an answer, but actually tries to provide some of what it is that they're thinking about when they give the answer. Right? Does that
yes,
have potential?
we did a little bit of that, but it can be very difficult to explain for most of the time it's just very difficult. So in the task we have like a box where they can enter their explanation for their prediction. So it's like a rationale for their prediction, and I think it was just a quality control mechanism, and we don't find that actually very, I mean, looking at this, I don't find this actually very useful, so yeah.
Okay, so I just have a quick question. Looking at your results earlier, you had some like 1,000 words and 10,000 words, and you've shown some improvement, but then if you're using all the words, there is some kind of a decline. Any?
Yes, so I mean, these are for different amount of data, so they are not very comparable. And so basically with more data, it's more difficult to get, so the cluster can be more complicated and hard to get correct. So I mean, the main thing is just to compare the baseline and the proposed.
Okay, if there are no more questions, let us thank the speaker again.